Hi, everyone. My name is Uni Nair, and I am a research strategist on Google's Responsible Innovation team.
And my name is Daryl Mason. I'm a strategic program manager contributing to the Responsible Innovation team.
In this tutorial, you'll learn how you can apply ethical principles when generating your own remote sensing datasets using machine learning. We'll walk you through an example of how responsible AI practices were used in the generation of the dynamic world dataset using Google Earth Engine data. But put more simply, we hope this workshop helps provide you with the tools that optimize positive outcomes by incorporating responsible AI guidelines and walking through a concrete example to help you see around corners. Dynamic World was created using Google Earth Engine and Vertex AI platform and is a 10-meter global dataset of land use and land cover updated in near real time. It uses the Sentinel-2 constellation by the European Space Agency and the Copernicus program, which generates a new global picture of the Earth's surface every 2 to 5 days. It is produced using a deep learning model, Vertex AI, and Google Earth Engine, a geospatial analysis platform to help scientists, researchers, and developers detect changes, map trends, and quantify differences on Earth's surface. The goal of Dynamic World Data Products is to enable reliable measurement of land cover and land use for positive environmental and social impacts, such as improved understanding of the human footprint, biodiversity, conservation, agricultural, and forest management. Using Dynamic World can help governments, companies, and researchers better assess, develop, and reach science-based targets to reduce greenhouse gas emissions per the Paris Climate Agreement. Critical to achieving Dynamic World's sustainable development impact is applying responsible AI practices. Dynamic World's users are primarily remote sensing researchers and developers who have been approved to work with Google Earth Engine. Approvals are made via a clear application process and clearly stated criteria for developer use, which states Earth Engine may only be used for development, research, or educational purposes. It may not be used for sustained commercial purposes without a commercial license, but may be evaluated in a production environment. Earth Engine was created to be a tool to advance scientific understanding of planetary processes to further environmental and social benefit. Its commercial use and preview with Google Cloud states its primary purpose is to understand and tackle critical sustainability and climate issues such as deforestation, water management, and sustainable land use. This clarity of language reduces the likelihood of Earth Engine and Dynamic World being used for any other purpose other than social benefit, and is a common responsible AI approach to safeguard against potential misuse. Even as we begin this tutorial, our description of the dataset illustrates a responsible data practice, which is to describe what the data contains, how it was sourced, clear attribution, and how it is intended to be used for social and environmental benefit. This information should offer relevant explanations to users. Google produced the Dynamic World model, source code, and dataset described in this tutorial for the Dynamic World project in partnership with the World Resources Institute and National Geographic Society. The Dynamic World dataset is provided under a CC BY 4.0 attribution license. National Geographic Society created the training data and consists of 24,000 plus Sentinel-2 scenes annotated by both expert aerial photo interpreters and non-expert annotators. This data is available under a Creative Commons by 4.0 license and requires the following attribution. This dataset is produced for the Dynamic World project by National Geographic Society in partnership with Google and the World Resources Institute. The World Resources Institute designed the land use and land cover taxonomy and plays a critical advisory role in the real-world usage and impacts this dataset can bring to bear for global environmental monitoring. As a developer, either building new ML models or applying existing ML for remote sensing, it's important to know the provenance of your data, the licensing permissions to use it, and the intended use cases.
This code lab assumes some familiarity with navigating Google Earth Engine apps. You may also wish to familiarize yourself with the code editor and Earth Engine API. Before proceeding, please make sure to first sign up for Earth Engine. Once your application has been approved, you will receive an email with additional information. Generally speaking, setting up a permission portal with a tracking process, such as a sign-in page that requests that individuals share their contact information, organizational affiliation, and intended use of the technology when assessing the platform, is a useful, responsible AI safeguard. It also helps in understanding whether there may be metadata signals that could be used to identify misuse. Additional information and deep dive into Earth Engine. Get familiar with the Earth Engine code editor, the IDE for writing Earth Engine JavaScript code in a web browser. If you're unfamiliar with JavaScript, check out the JavaScript for Earth Engine tutorial. If you're unfamiliar with the Earth Engine API, check out the Introduction to the Earth Engine API tutorial. Once you're familiar with the Earth Engine, get started on the code lab. This section of the tutorial walks you through critical steps to apply ethical decisions as you code, using the example of Dynamic World. The Dynamic World dataset contains per pixel predictions of 9 land use land covers classes as described in the table below. Land use describes how humans use the land, whereas land cover describes the physical material on the surface of the earth. Images in this dataset includes 10 bands, 9 bands with estimated probabilities for each of the 9 DW land use land coverage classes, and a class label band indicating the class with the largest estimated probability. These distinct properties enable users to do multi-temporal analysis and create custom products suited to their needs.
This use of predictions in Dynamic World went through an ethics review in which it was evaluated for safety, scientific rigor, fairness, potential misuse, and of course, social benefit. In this case, for alignment with Google's AI principles, which serves as our ethical charter. You may consider setting up checkpoints in your ML project to evaluate how the technical decisions you have made align with your organization's mission, statement, values, or ethical charter.
Thanks, Uni. In the case of Google's AI principles, we were careful to state applications we would not pursue. A clear set of principles can help you make decisions as a developer with your ethical goals in mind. When creating a product like Dynamic World or related derivatives, it's important to reflect on ethical implications and downstream societal implications when used at scale. Considerations could include if the dataset is based on scientifically sound foundation, if there are potentially negative environmental impacts when used, how it could promote discrimination or be misused by malicious actors along the way. It is also critical to consider how the model is intended to benefit the user or society. For example, does it drive greater efficiencies, help contribute to a sustainable development goal, or drive greater user agency? For Dynamic World, the model could benefit users such as scientists because it helps them create a land cover derivative maps that focus on a specific time and geography. And it could gain near real-time intelligence on flooded areas, crop rotations, forest extent, and help quickly predict transition in land use over time. It can also help governments or companies identify the impact of an event or decision on the landscape, which can drive more accurate tracking, measurement, and reporting against sustainability commitments. It's equally important to understand the limitations of the model, if any. In the case of Dynamic World, human expert markup of land cover in a single satellite image can take hours, which can impact scalability. Manual labeling of 8+ petabytes of data, especially as it's produced in near real time, is not realistic or feasible. Second, land cover is not a binary output, and each pixel represents a mix of classes, a combination of trees, grass, or scrubs, which illustrates the world much more accurately. Third, it's hard for users to analyze single scenes because of clouds, shadows, and data inconsistencies. Dynamic World includes a cloud shadow mask that prevents cloudy scenes from being mislabeled. Dynamic World includes predictions across all 9 land use land cover classes and displays a single top 1 label for each pixel. The real world is a mix of many land use land cover classes at any spatial resolution. In this exercise, we'll examine how to visually interpret predictions over space and time. Load in Dynamic World. In the search field, enter 7 de Setembro, Brazil. You should see Dynamic World data compute for the indigenous territory of the Paire Suri people who live in the 7 de Setembro region of Brazil. Set the start date to 2016, January 1st, and the end date to 2022, January 1st. Click on the Update button. This may take a few minutes to load as it's computing on the fly. Click on Point Anywhere on the map, and a chart will generate on the fly. Zoom further in for a faster response. Examine the chart where clash probabilities on the y-axis and time is on the x-axis. In the example, the top 1 clash prediction from January 1st, 2016 to July 27, 2017 is trees, varying from a probability of 0.684 to 0.755. By the time the next Central 2 scene is captured on September 5th, 2017, the prediction is no longer top 1 trees, and the signal becomes more noisy. Enlarge this chart by clicking the icon on the top right corner. As we've learned, there are a lot of opportunities to use Dynamic World for tracking landscape dynamics across years or interannually. Now let's ask ourselves about responsible practices to apply when examining probabilities per pixel in Dynamic World or creating derivative products from Dynamic World. While there are already weekly forest alerts products in Global Forest Watch, Dynamic World gives us the ability to detect changes in the landscape or areas outside of forests. With ecosystems changing dynamically, our ability to monitor the surface of the planet has to be dynamic as well. This is particularly notable in places like the Amazon. But what's happening on the ground can help local communities adjust to the changing conditions and bring visibility to challenges in managing natural resources. Dynamic World does not reveal any visual data regarding people. Protecting privacy, and from a broader standpoint, inferences are limited to shield against covert surveillance of larger populations or communities. Dynamic World's 10-meter resolution inherently safeguards against potential misuse. As Sentinel satellite imagery is already available in the Earth Engine data catalog, and visual inspection of change in the landscape over time is available for civil society to directly observe, Dynamic World offers the additional capability to quantify pixels in near real time for the 9 land use land cover classes and produce derivatives when combined with local data. The training data, model, or platform is also protected against use with other unsanctioned technologies. The real-time updates are so computationally intense that it has to be used within Google Earth Engine and can be easily monitored for irregularities. It's essential to be mindful of the safeguards to implement when creating a near real-time dataset, such as Dynamic World, to address potential environmental and social harms, such as targeting areas for deforestation, resource extraction, or exploitation of vulnerable communities. Examining model limitations is an important practice for any remote sensing product that uses machine learning. In the case of Dynamic World, it's important to understand where the model does not perform as intended, defined as where humans would label a pixel differently than the ML model. For example, we have a very robust cloud masking procedure incorporating cloud removal and cloud shadow removal algorithms. but we do have some cloudy pixels that are missed. Looking at the time series and source imagery can help avoid unexpected results due to missed clouds. This illustrates Dynamic World's potential to generate map derivatives across the available space and time span while meeting Google's AI principles to uphold high standards of scientific excellence. And it's important for you to consider what's the right thresholds are in your use case.
Dynamic World is an example of how, put to the right uses, AI can help scale humanity's ability to meet the environmental challenges of the 21st century using data-driven, science-based methods. The lessons learned in the AI Principles Review process are also generalizable when applying ML for remote sensing use cases. Even when applying ML in socially beneficial use cases, responsible AI best practices can be critical to amplifying those benefits and also as lenses to see around corners and potentially harmful impacts. For example, in Dynamic World's instance, the AI Principles Assessment helped identify possible environmental or social harm, such as target areas for deforestation and resource extraction. Key to considering ethical impacts is proactively reflecting on the context of the ML remote sensing technology in the following 4 categories. Number 1, the end use. Number 2, the user. Number 3, the impacts. And number 4, the safeguards or mitigations measures. Starting with end use. It might seem obvious, but being clear from the outset on what the intended use cases are and what problem you're trying to solve for or hope to achieve by creating your technology is really important. For example, will it be deployed in a specific geography? Is it publicly available versus private, et cetera, et cetera? One consideration is if the use case leads to the collection of new data, if it includes sensitive characteristics or proxy information, and what outcomes are generated from the use case. Another is, will automated decisions be made, or will there always be humans in the loop? In other words, who views the analysis and for what purpose? Number 3, can the information captured be combined with other information sources that might compromise privacy or security of individuals? And finally, are there unintended use cases or results that might occur? This visibility helped us work with the development team to implement safeguards we'll cover later in the workshop. Number 2, the user. Consider your target users and what ethical implications might come into play, as they can be significantly different between the public sector, private industry, or individual users. Considerations can include where the users operate, and is there a strong rule of law in those geographies? What individuals, partners, populations, or communities does the user interact with regularly, and who will be impacted by the technology? How have similar users approached the use and deployment of new technology in the past? It's important to consider if any of your target users might be inclined to misuse or abuse technology tools. Third, the impacts. What ethical risks and opportunities are relevant for this use case? For example, can they be fairness related, have privacy implications, safety implications, or security related? Or it could even be related to the Sustainable Development Goals. Pausing to consider the severity of these risks is critical. For example, thinking about the number of people that can be impacted, the seriousness of the impact, and if something were to happen, how easily things can be fixed once it's released out into the world is important. In most cases, it's pretty hard to fix something after the fact, which makes thinking of these things proactively that much more important. Next, do certain individuals, markets, regions, user segments, or populations present higher risks of negative consequences versus others? such as migrants, women, children, elderly, people with mental health issues, different races, ethnicities, or nationalities. This then helps you determine various safeguards that would make sense. For example, a reporting channel for users to report negative impacts of the use case or misuse or abuse is something that Dynamic World is employing. And finally, identify appropriate safeguards or mitigation measures. This includes knowing the role of the developer, whether it's Google or it's one of you, that might encourage, support, incentivize, motivate, or enable the user to cause an adverse ethical impact.
Identifying those safeguards or mitigation measures is really where everything comes together and is worth emphasizing. It may seem like a simple task, but even though societal needs are more or less the same, the most effective tools and channels to achieve success are constantly in flux as social norm evolves, technology advances, and development considerations become more complex. Even with the best of intentions, we're constantly reminded of the unintended real-world consequences of technology. But by adopting an ethics by design mindset, you can safeguard against a lot of negative outcomes while also amplifying the social good your work can have.
That's a great call out, Daryl. As developers of that technology, it is in your control to ensure positive intent is optimized by considering all possible outcomes and impacts. Sometimes the most socially beneficial technology can be the most easily adapted for the opposing uses. For example, in Dynamic World's case, we weighed the possible trade-offs of how the technology could be potentially used for extractive purposes instead of environmental protection. Scenario planning helped us see around these corners and implement proactive measures that would alleviate unintended uses. Some examples include taking steps to promote transparency. At Google, and in Dynamic World's case, that included completing an ML onboarding toolkit, which is related to our model and data card initiatives. But whether it's in the form of a formal artifact, like with Dynamic World, or otherwise, any developer should take steps to explain how your use case works, what it can and can't do, and what it should not be used for. One useful way of doing that is through a terms of use. Specifying intended usage and articulating prohibited uses. Whether using a terms of service or something similar, identifying green and red flag uses is useful for any technology where the scale of impact and potential severity is high. In a similar vein, a statement of intended use or purpose could be used to encourage appropriate usage and also the technology's limitations. It's also important to note that there's no way to scenario plan for everything, so to also include mitigation measures that can help identify and address issues as they occur. For example, developing a reporting channel and promoting the existence of this mechanism could help impacted people or communities report misuse. Next, track usage or users. Consider setting up a permissions portal with a tracking process, such as a sign-in page that requests that individuals share their contact information, organizational affiliation, and an intended use of the technology when accessing the platform. This could help you explore whether there may be metadata signals that can be used for identifying misuse. Targeted outreach to good actors would be useful to creating and maintaining relationships with key users. This can enable better visibility into how the technology is used in practice and how use cases evolve over time. This can also encourage a more systematic way to ensure your technology is in the hands of actors who use it for good. Last but not least, we wanted to give a special thanks to the Dynamic World team and the partnership with World Resources Institute, Earth Engine, and Vertex AI teams for their ongoing engagement and support of responsible AI and sustainability. Thank you.